Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at transformation of single random variables. This is going to be a two-part video lecture. Today we're going to look at what I call the forward problem. In part two we'll look at what I call the inverse problem. I'll get to what I mean by that in just a few minutes. So, remember that x as a random variable is a function. X, if x represents a random variable, x is a function. It's a function that maps an outcome of a chance experiment to a real number. All right? All right. X is a function. A function of a function is a function. Remember that from probably an early calculus or maybe even an algebra class. A function of a function is a function. Sometimes we call that a compound function. And since a random variable is a function of a random variable is another random variable. If a random variable is a function that assigns outcomes of a chance experiment to a real number, if random variable x is a function, and a function of a function is a function, then a function of a random variable is another random variable. All right? So, if x is an initial random variable, then y, which is some function of x, is a new random variable. All right? The transformation function, let's just call that with an arbitrary argument, g is what's going to be known as my transformation function. All right? All right. So a function of a function is a function. A random variable is a function. So a function of a random variable is another function. We're going to look at what happens when we take one known random variable, say x, and apply a transformation function g. We're going to look at what we can determine about my new random variable y. So let me define what I mean by my forward and inverse problems. One, we'll pretend that we're given the probability density function for x or the cumulative distribution function for x and the transformation function g. We're going to be given the probability density function and or cumulative distribution function for x and the transformation function g. And the question that we're going to ask is, what is the probability density function for y and or cumulative distribution function? Oops. That would be sub y and or the cumulative distribution function for y. So given the probability density function and or cumulative distribution function for x and the transformation function, the question we want to ask is, what is the probability density function and or cumulative distribution function for y? All right, this is what I call the forward problem. Addressing the forward problem will be the topic of today's video. A similar problem is this. Given the probability density function for x and or the cumulative distribution function for x and the probability density function for y and or its cumulative distribution function, given an initial probability density function and or cumulative distribution function in x and a finishing probability density function for y and or its cumulative distribution function, the question is, what is the required transformation function y equals g of x? What is the transformation function? This is what I call the inverse problem. And we will address that in the video which follows this one. This will be, addressing the inverse problem will be part 2 of this lecture series. Okay? All right. Let's address the forward problem. Forward problem. We're going to piece this together. It'll take us, we'll do this in 3 different parts. The first thing I'm going to do is I'm going to assume that, g of x is monotonic. Monotonic, meaning that it's always increasing or always decreasing. All right? In the upper right-hand corner of the screen, I'm showing you a monotonically increasing function. We'll look at a monotonically decreasing function in just a few minutes. Okay. For a monotonic function, for each x value, there's only one corresponding y value. Okay? Pretty clear. So for example, over here, I've got an x naught, and there's exactly one value of y naught. Okay? All right. All right. So let's first consider that g of x is increasing. And then let's notice a few things. The probability that y is less than or equal to some point y naught, that's clearly the cumulative distribution function evaluated at y naught. Let's see if we can reason this out by looking at my figure. The probability that y is less than y naught. Since I have a monotonically increasing function, I hope you'll agree with me that that is equal to the probability that x is always less than or equal to x naught. For values of x less than x naught, I end up with a value of y less than y naught. Since my function g is always increasing, the probability that y is less than y naught, which is the cumulative distribution function evaluated at y naught, is equal to the probability that x is less than or equal to x naught. And that equals the probability, the cumulative distribution function of x evaluated at x naught. All right? So, more generally, I can make this statement. More generally, the cumulative distribution function for y equals the cumulative distribution for x if I everywhere substitute x equals g inverse of y. Remember that my random variables are going to be related through a transformation function y equals g of x. Just a second, I almost made a mistake. Y equals g. Come on, Brad. Y equals g of x, or x equals g inverse of y. Why do I need to be really careful about this? I'm looking for a cumulative distribution function for random variable y, and it must be a function of little y. My cumulative distribution function for x is a function of x. I need a function in y. I can make it a function in y if I everywhere substitute x equals g inverse of y. So, the cumulative distribution function for y follows the functional form for the cumulative distribution function for x if everywhere I have an x, I substitute g inverse of y. Now I end up with a function in y. Okay? All right. What about the PDF? The PDF is found by taking the first derivative of the cumulative distribution function. And now I'm going to apply what I hope you recall as the chain rule. This is going to be the derivative with respect to x of the functional form for the cumulative distribution function of random variable x times the derivative of x with respect to y, where, always and everywhere, I substitute x equals g inverse of y. Okay? More explicitly, I will have the, when I take the first derivative of the cumulative distribution function in x, I get the probability density function for x times dx dy, where I make the substitution that x equals g inverse of y. And one last step, I'll summarize this once I get through a little bit more math. This is going to be the probability density function, functional form for x, substituting in g inverse of y, times the derivative with respect to y of g inverse of y. Once again, I get a function in y. All right? I'll summarize this for you in just a few minutes. I'm going to do a bunch of examples. On this page, though, this is the final result. And let me extend this down just a bit. This relationship here is the final result. I'll summarize that for you in just a few minutes. Okay. What about if we have a monotonically decreasing function? We have to take account for that separately. So, all right. Now I hope you understand that the probability that y is less than y naught equals the probability that x is greater than x naught. All right. The probability that y is less than or equal to y naught equals the probability that x is greater than x naught. But this is the cumulative distribution function of y evaluated at y naught. And this, the probability that x, random variable x, is greater than x naught is 1 minus the cumulative distribution function for random variable x evaluated at x naught. Okay. More generally, we would then have that the cumulative distribution function for y, for any arbitrary value little y, equals 1 minus the cumulative distribution function evaluated x, when we always substitute x equals g inverse of y. All right? Or that is one of our final, I made a mistake. That is a cumulative distribution function. I made it look like a probability density function. That is a cumulative distribution function. That's a capital F. And this is the final result so far. All right. If g of x over here is an always decreasing function, then the cumulative distribution function for y is 1 minus the cumulative distribution function for x, the functional form for the cumulative distribution function for x, where I always and everywhere substitute g inverse of y for every little x. We can then find the PDF by taking the first derivative. And that's supposed to be a lowercase f, PDF. When I take the derivative of 1 here, I clearly get 0, and everything else follows just like it did on the previous page, and my minus sign right there translates into a minus sign right there. And what I find is that my probability density function for y equals the probability density function for x times the derivative of x with respect to y. Oh, forgot my minus sign. There's a minus sign out front. And I always substitute x equals g inverse of y. All right? Now, here's something you need to observe. Remember, there's a minus sign right there. There's a big minus sign right there. The derivative of x with respect to y, this is always negative. It's always negative in this case. Remember, we're looking at a monotonic g of x function that is always decreasing. Okay? It's always decreasing. If I came over here and reversed the axes for x and y, I would have a function that is decreasing. The slope, the derivative of x versus y, where x equals g inverse of y. This derivative, the derivative of x with respect to y, when x is the inverse of my transformation function, it's always a negative function. It's always a negative derivative. Okay? So, I get g of x is always decreasing, then what we have for the probability density function all right, that minus sign which multiplied or which preceded the probability density function for x, that can be absorbed into the derivative of x with respect to y, and we can just call that an absolute value. It makes, if g of x is an always decreasing function, then the derivative of x with respect to y is always negative. Multiply that times a minus sign, I get the absolute value. Okay? So, in summary then, I have the following relationships. The cumulative distribution function for y equals the functional form for the cumulative distribution function for x, where everywhere I substitute in x equals g inverse of y. This is a true relationship if g of x is an always increasing function. And so that's my first final result. My second final result is that my cumulative distribution function for y is 1 minus the functional form for the cumulative distribution function for x, where everywhere I have an x, I substitute in a g inverse of y. And this is true if g of x is a always decreasing function. And my third result is that my probability density function for y equals the probability density functional form for x, where everywhere and always I substitute g inverse of y for x, and I take the derivative, or multiply times the absolute value of the derivative, of g, multiply times the absolute value of the derivative of g inverse of y with respect to y. And you'll notice that in the first case, when g is always increasing, the derivative of x with respect to y is always positive. Go all the way back to this figure. The derivative of x with respect to y would always be positive. Absolute value of a positive number is a positive number. All right? So this covers everything. This is the final set of results for the forward case. Okay. Let's do some examples. Let's let my transformation function y equals g of x be a linear transformation. Ax plus b. All right? This is known as a linear transformation. Okay? And I'm going to let x be an exponential random variable with a PDF that looks like this. All right? This is an exponential random variable. Keep in mind that random variables are most commonly described by their probability density functions and cumulative distribution functions, and not the mapping function that maps outcomes of chance experiments to real numbers. We almost never talk about the random variable in its functional form, which maps an outcome to a real number. Instead, we talk about a random variable in terms of its probability density function and or cumulative distribution function. All right, so our goal is to find the probability density function for y. All right, that's what we're looking for. Well, recall that is the way we do the transformation. So the first thing we need to find is the inverse of g. So x equals g inverse of y equals, very simply, 1 over a times y minus b. That's it. And so the absolute value of the derivative is 1 over absolute value of a. And strictly speaking, a can be positive or negative. We're going to look at both cases. All right, we're going to look at both cases. I could have a linear transformation where the slope a is positive or where the slope a is negative. All right, so I need to maintain my absolute values in the derivative of x with respect to y. All right. If, we're going to look at two cases. If a is positive, we just start making some substitutions. All right. I can drop my absolute values because I'm declaring that a is positive. I'm going to get an alpha over a times e to the minus alpha. Now where I have an x, I have to substitute in g inverse. I get y minus b over a. And then I have to also substitute y minus b over a in my step function. All right? Make sense? I'm going to rewrite this one more time. I'm going to say alpha over a e to the minus alpha over a y minus b times step function of y minus b. Division by a positive constant in a step function doesn't matter. Okay? The step function becomes unity when the argument is greater than or equal to 0. All right? In this case, the argument becomes greater than or equal to 0. The step function becomes 1. For y greater than b. Okay? Division by a positive constant inside of a step function just doesn't matter. A step function becomes unity when the argument is greater than 0. In this case, it becomes greater than 0 when y is greater than b. Okay? Let's look at the case when when the slope a is negative. A little more interesting. If a is negative, once again, my derivative with respect to derivative of x with respect to y is 1 over absolute value of a. I better carry my absolute values now because a is negative. And my my probability density function looks something like this. Alpha over absolute value of a times e to the minus alpha over a. You'll notice that, let me finish y minus b. You'll notice that I don't use the absolute value of a in the exponential. There I'm simply substituting x equals g inverse of y. There's no absolute value in the exponential. And then I still have to write down u of y minus b over a. Now this step function we have to examine just a little bit more. I said earlier that division by a positive constant doesn't matter, but in this case we're dividing by what we know is a negative constant. So we have to examine that just a little bit better. So u of y minus b over a can be written as u of y minus b over negative absolute value of a in this case. And that can be written as u of b minus y over absolute value of a. And now we're dividing by a positive constant, which simply doesn't matter. And this can be simplified as u of b minus y. In all cases, my step function is unity when the argument is greater than 0. So in this case, let's write that a little bit better. That's what my step function u of b minus y looks like. Okay? All right. If u of y minus b turns on at b, u of b minus y turns off at b. Okay? So, to finish up this particular part of the problem, if a is less than 0, it's a negative going slope, then my probability density function for y equals alpha over absolute value of a e to the minus alpha over absolute value of a times b minus y times u of b minus y. You'll notice now I put in absolute values around a in the exponential, but I reversed b and y also in the exponent. And as a summary, if a was positive, my probability density function was what? Alpha over a e to the minus alpha over a y minus b u of y minus b. Okay? Those are the two probability density functions which result when we take an exponential random variable and apply a linear transformation. Depending upon the slope of the straight line transformation, we get two possible results. Here are two figures demonstrating the result of this transformation. The blue curves are my initial exponential random variable under the condition that alpha is 3 in both cases. Alpha is 3 in both cases. So you'll notice that the peak of my initial exponential curve is 3 in both cases. All right. My initial exponential random variable turned on at x equals 0. For these two curves, I'm showing a scale, a horizontal scale of y, but you'll have to understand that for the blue curve, that was a function in x. That was a probability density function for random variable x, and I'm plotting it on the same scale. You'll just have to kind of forgive me for that. So if the parameters for my example are that a is 2 and my offset is 4 for b, and in this case a is positive, then what we find is that my transformed random variable probability density function is shifted up to 4. It's the peak is divided by 2, so the peak is now down to 1.5, and it still trails off exponentially. On the lower right hand side, still we're dividing by 2, but a is negative. My offset for my linear transformation is still 4. In this case, because of the reversal of that step function, my transformed random variable ends at 4, and the peak is 3 divided by 2, or 1.5. Okay? All right. Next question is, what if G is not monotonic, meaning that it has positive going and negative going regions? All right? I'm not going to get into a long discussion of this. I'm simply going to write down the result, and hopefully it'll make sense. Basically, you do the transformations over each monotonic region. You do a transformation over each positive going region and each negative going region. So you do the transformation over each monotonic region, and then you add the results. That's basically it. All right? Now, I'm going to write down a function to kind of quantify this. And it's a quasi-function. I don't want you to get too worried about this. But just let me sort of summarize it this way. The probability density function for y will equal the summation over each monotonic region of the probability density function for x in each monotonic region this is only a quasi-function. There's going to be one probability density function for x. All right, we have an input probability density function. There's only one of those. But we might have multiple monotonic regions. All right? All right, so what we do is we find the absolute value of the derivative of x with respect to y, where x equals g inverse of y in each monotonic region, increasing or decreasing. We do the transformation according to the usual steps. We add up the results and we get our final probability density function for y. A lot of words. Basically, you do the transformation over each region, add up the results. It's easier to demonstrate by example. All right. We'll do a couple of simple examples just to kind of demonstrate the point. Let y, my new random variable, equal a x squared. And in this case, I'm going to let a be positive. All right? All right. So my transformation function looks like this. Right? For any value of y, say y naught, there are two values of x, plus or minus x naught, which can give rise to y naught. All right? And I have over here, I have a always increasing function, a monotonically increasing function, and over here I have an always decreasing or monotonically decreasing function. So what I'm going to do is I'm going to do the transformation over each of those two regions and add up the results. All right? So the fact that there are two possible values for x for each value of y should give some evidence to you that I'm going to sort of double the probabilities of being in the region plus or minus x naught. Simply going to add up the results. All right. We're going to assume now that my probability density function for x is a zero mean Gaussian. It's going to be this, 1 over sigma square root of 2 pi e to the minus x squared over 2 sigma squared. So this is a zero mean Gaussian. Happens to be centered at the origin. It's symmetric about the origin. Looks something like this. And it's got a standard deviation of sigma. Okay? All the symmetry in this problem is going to allow us to simplify our results pretty substantially a little bit later on. All right. So, first thing we do, we have y equals ax squared. We can invert this, and we come up with two results. x1 equals the positive square root of y over a for the region y greater than 0. And we have x2 equals negative square root of y minus a in the region y is less than 0. All right? It's real important at this point that I point out something for you. Although x can be plus or minus, the zero mean Gaussian has x values that are both positive and negative. Up here, y is always greater than or equal to 0. Y has no negative values. That's really important. Excuse me. This should be x greater than 0, x less than 0. All right? Not y. Y is always positive. Y is always positive. That's going to be important in just a minute because we're going to have some step functions that we have to introduce into our result. So the next thing we have is we need to take the derivative, absolute value of the derivative, absolute value always means I end up with a positive result. That's going to be 1 over 2 times the square root of YA, and this is true for both regions. Okay? That's true for both regions. All right. So, let's do our transformation. Our transformation is going to be this. I'm going to have two pieces. I'm going to have 1 over sigma square root of 2 pi e to the minus y over 2 sigma squared a times 1 over 2 times the square root of YA, and here's where my step function comes in, u of y. Okay, so here's the step function, and I've got to add another piece to this in just a second. This is because the result y is always greater than or equal to 0. This piece here is the absolute value of my derivative. This is my zero mean Gaussian, where everywhere I had an x, I substituted in y. G inverse of y, rather. All right? Then I have to add in the second piece. All right. Due to all of the squaring and the symmetry of the problem, I end up with the two transformation pieces are actually end up identical. Once again, we can just say that this first part is the transformation when x is greater than 0, and the second part is the transformation when x is less than 0. Due to the squaring in the exponential and due to the symmetry of the zero mean Gaussian and the symmetry of the transformation function itself, the transformations over each of the two monotonic regions, the increasing region and the decreasing region, they end up being identical. I still add them up. Okay? And we can simplify this a bit. I can pull out the common stuff. This is my final result. And you'll notice, once again, I keep bringing this up. My step function here does not come about because of any mathematics that I'm done. It comes about because I recognize that in all cases, due to the transformation, y is positive, so I have to throw it back in there. My, my transformation function, my transformed probability density function is simply not valid if y is less than 0. Okay? Well, this result for this particular example is plotted here under these conditions. I plotted it assuming that, once again, I have a zero mean Gaussian random variable. In the solution that I did on the previous page, I had not specified a standard deviation. Here I just assume sigma is 1, and I let a equals 1. All right. So what we see is that y is always positive. Y is always positive, has no value less than 0. And then it does shoot off towards infinity as y approaches 0. Okay? But that's what that would look like. All right. One more example, and we'll call it a day. Let's assume, in this case, that my transformed random variable y is a constant times x if x is positive and 0 if x is negative. That's what my transformation function looks like. And we're going to assume for this particular example that a is positive, the positive going slope. All right? So there is a region over which my transformation function is always and everywhere 0, and it's a linear function with 0 offset and slope a when x is positive. Next thing I'm going to assume is that probability density function for x, is a zero mean Gaussian. It's a zero mean Gaussian. All right, my probability density function for x will look something like this. All right, symmetric about the origin. That's very important. All right, so let's do the transformation. We're going to do it over two monotonic regions. We've got a region which is always increasing, and we have another region for x less than 0 where y just equals 0. So for x greater than or equal to 0, x equals y over a. That's my G inverse. And my absolute value of dx dy is just 1 over a. I don't have to worry about keeping up with absolute value signs because I've assumed that my slope is positive. All right, so for the x greater than or equal to 0 range, I simply have that my probability density function is 1 over sigma a square root of 2 pi e to the minus y squared over 2a squared sigma squared. And once again, I have to throw in a step function because in the region for x greater than 0, in the region where x is greater than 0, y is also greater than or equal to 0. That is the origin of this step function. I have to be clever about that. I have to watch for it. All right? So this is the first piece of my transformed result. Okay? What about the lower region? What about for that region? Well, very simply, by symmetry of the problem, go back and take a look at this. By symmetry of the problem, x is 50% of the time less than 0. So 50% of the time, y is 0. Let's acknowledge that fact. The probability that y is exactly equal to 0 is the probability that x is less than 0, and that's exactly equal to 1/2, because I had a zero mean Gaussian. Due to the fact that my input probability density function was a zero mean Gaussian, it's exactly 50% likely that my random variable y equals 0. So the way we handle this, and this is very important, the probability density function for y at 0 equals 1/2 times delta function. All right? What that means is this only has value at y equals 0. Okay? And you'll also recall one of the defining properties of a delta function is that if I integrate from minus infinity to infinity of a times delta of x minus x naught dx, the result is a. Okay? The area under a delta function is its strength. Okay? So for this particular example, I can summarize my probability density function this way. I get 1/2 delta function at y. That's not equal. That's plus. Then the rest, I get 1 over a sigma square root of 2 pi e to the minus y squared over 2a squared sigma squared u of y. This half is for x greater than or equal to 0. This is for x less than 0. And then if I plotted this, it might look something like this. I'm going to use a couple of different colors here. I'm going to have a delta function sitting right at the origin. That's supposed to be in red. I'm going to have a delta function sitting right at the origin. Its amplitude is 1/2. I'm going to locate exactly 50% of my probability at the origin. And then the other piece will look something like that. Okay? And clearly this is 0. Y can never be less than 0. It can be exactly equal to 0. It's 50% likely to be exactly 0, but it can never be less than 0. And the probability density function governing positive values of y is, again, another Gaussian function. All right. I know that was a long video, a whole lot to cover, but that's it for today. As usual, if you have any questions, please do contact me at your earliest convenience, and I will answer all questions as fully as I am able. Have a nice day. Bye-bye.